Exercise 230 is asking you to draw a resonance structure for this compound, and that compound is called 2-heptanone, and it's in some kind of cheeses. If you ever take a block of gorgonzola cheese and just take a big whiff of it, the main thing, lots and lots, literally dozens of molecules, if not hundreds, are entering your nose, different molecules. But one of the ones that you'd be perceiving the most would be this 2-heptanone. So, is this involved in resonance? Well, in order to see, we want to go through each of these resonance patterns methodically, one by one. We haven't gone through this fifth one yet, so that's not relevant for this problem, or this exercise. But in order to go through those problems, those patterns, they'll be easier to see if we draw in the lone pairs first. Now, none of the carbons have lone pairs because carbon only has lone pair if it has a negative charge, and none of these carbons has a negative charge. The oxygen, though, has only 2, 4 electrons around it, and so it needs 6 and 8. All right, so now we can go through these. First, do we have an allylic lone pair? We have a lone pair, but the lone pair is on an atom in a double bond, not one atom away from an atom in a double bond. So it's not allylic. Do we have an allylic positive charge? No positive charge anywhere in sight on this molecule. Do we have a lone pair adjacent to a positive charge? And we have a lone pair, but it's not next to a positive charge, so we don't have that pattern. How about a pi bond between two atoms of differing electronegativity? Well, we've got a pi bond. Remember, a pi bond is every bond after the first bond, so double bonds, triple bonds, those are flashing lights that you've got a pi bond. So we've got a pi bond here, and it's between an oxygen and a carbon. Oxygen is one of those electronegativity heavy hitters. It has huge electronegativity. It pulls electrons to itself very forcibly. Whereas carbon doesn't do that quite as much. And so we have a pi bond between atoms of differing electronegativity. So we've got resonance. Well, let's go sing it on a mountain. We've got these big brackets here to warn everybody. And then inside we're going to draw our molecule, but the big brackets are telling everybody the true molecule is neither of the molecules we're going to draw. It's the average of the two. So here is our molecule. There's the resonance setup. Whenever you have a pi bond between atoms of differing electronegativity, the electrons in the pi bond go toward and go onto the more electronegative atom. So you would take that structure, redraw it as it is, but anywhere where there is the tail of a curved arrow, those are electrons that are moving away from there, so you erase those. And anywhere where there's the head of a curved arrow, those are electrons that are arriving there, so you draw them in. And if the head of a curved arrow is pointing at an atom, you draw them as a lone pair. So we'll fill in 2 dots there. You have that lone pair. Now if you find the formal charges, notice on oxygen it's 6 minus 6 dots and 1 line, so 6 minus 7, that's -1. And for this carbon it's 4 minus 0 dots, 3 lines, that's +1. So there's your resonance structure. The true structure never looks like this and never looks like this. It only, always, looks like the average between the two. So something like this. The bond between the carbon and the oxygen is not single or double, it's something in between. And the oxygen doesn't have a 0 charge, it doesn't have a full negative charge, it has something in between. And the carbon doesn't have a 0 charge or a positive charge, full positive charge, it has something in between. And because this has resonance, that means the molecule is more stable and more rigid. So it would serve as a better chemical messenger. And lo and behold, it does. It is a chemical messenger communicating a certain type of smell, both to people, who then find it appetizing, and also this smell has been found in the urine of rats, among other places. And it's apparently, when rats are stressed, they pee out this molecule, or this molecule is found in their urine. And that lets other rats know that that rat is stressed, so, maybe don't hang out in the same place that rat is hanging out in. And they get that message so well because this molecule has resonance.